If you're on the CS side of TikTok, you might have seen this video.
Dude, she was using infinite recursion. Hey, what's up? Need some help? Oh no, I'm not a TA, but I can help you out. Let's see. Is your project code? Oh, cool, let me check it out. Is that infinite recursion? Dude, your noob is fun!
In the video, he makes fun of infinite recursion, which is a problem that many beginner programmers face, especially when they first try to recurse. Infinite recursion occurs when you have a function that calls itself endlessly over and over again without ever reaching a base case. The only way to stop this is when you either have a Stack Overflow or your program or your computer errors out and crashes. Well, this got me thinking, is it possible to have infinite recursion but still have it be safe? And would that ever be useful? Well, let's answer the second question first. Yes, it is useful. Consider the example of having some sort of infinite scrolling feature. You might need to recurse infinitely. Or say if you have to find the nth fib number, and you want to find it for really big n's, well, you might need to use infinite recursion to get up to that level. So this brings us to a new paradigm in computer science called lazy programming. And this also gives us a whole lot of new terminology to think about infinite recursion in a different way. Lazy programming is any time you program so that computation is delayed until it needs to be actually evaluated, which kind of fixes the issue of infinite recursion. Let's look at some terminology now. So the first word we're going to look at is called a thunk. A thunk is just another word for a special type of function that takes in a unit type as an input. This way, thunks are forced to not be evaluated until you call it on a unit type. By using thunks, we suspend computation until we have to have it evaluated. Another aspect of lazy programming is an infinite data structure that helps us facilitate delayed computation. This is called a stream. Streams are really cool. You can think of them kind of like an infinite list, but they have their own parts and terminologies alongside them. So streams basically, by the formal definition, is just a suspension of a front. And a front, well, a front is kind of like the head of your list or the head of your stream. This data type, a stream, allows us to recurse infinitely because it, as a data type, is infinite. Now let's look at the definition of a stream in order to better understand it. The way a stream is defined in SML is we have a type of an alpha stream being something. So we don't have to define it because we don't care what the actual type is. Then we have a data type of an alpha front, and this is either going to be empty, so we have an empty front or an empty stream, or it can be the cons, where cons is just kind of the connector of the alpha, whatever type our stream is made out of, and an alpha stream. Well, basically, if you look at this, it's a very recursive data type. A front is either something attached to a stream, where a stream can be anything, or it's just empty. We also have two really important functions that help us do a lot of the computation on streams. The first one is called delay. And all this does is it lets us delay our computation. The type of delay is it takes in a thunk and it returns to us a stream. So basically it just passes on the thunk without doing anything to it. We also have expose. Exposing is a bit of a tricky line to walk because you don't want to expose too much because then you lose the power of lazy computation, but you also need to know when to expose. So all expose does is it reveals a front. So it has type stream to front. Note that if we call expose on delay of some f, we should get back f because delay and expose are kind of opposites. So now let's look at some infinite recursion with our data type. We're going to be coding the blum blum shub pseudo-random number generator. Let's first take a look at our stream code. So we have our data type here, where we have our alpha stream, which is made out of a unit to alpha front. And then we have our alpha front, which is of type either empty or cons of an alpha star alpha stream. So as you can see, because of the and here, it is mutually recursive, which means that it's basically infinite. We also have delay and expose. So delay is just a stream, it just returns a stream. And expose takes in some sort of stream and just returns the stream called on a unit. Kind of reminds us of thunks, right? There are other stream functions, but these are some of the main ones that we need to use right now. So now let's look at our Bbs function, the blum blum shub random number generator. You don't need to understand what the actual number generator is doing. You just need to understand what the code is doing. So let's take a deeper dive into this. We have our function Bbs, and Bbs takes in m, which is some sort of starting number, which is the multiplication of two primes, and we have s, which is a seed for our number generator to start off with. The first thing that we do anytime we have an infinitely recursive function is we call stream delay, because we don't want to do anything until we actually want to expose the front of our stream. So we delay it. And delay, as you know, takes in a thunk. So we pass it a thunk as a lambda. So we give it a type unit, and then rather than doing anything else, we just pass it on to our mutually recursive function, which is called Bbs prime. So with Bbs prime, we just pass in our two input values, the multiplication of two primes and the seed value. So literally all line 3 is doing is it's just pausing the computation and letting the helper function, the prime helper function, deal with the actual math. Then on line 4 begins the mutual recursion. We have and here, which shows that, and we have our Bbs prime function, which also takes in the same two numbers, and here we're generating this new stream. So we have a cons of this calculation right here, which is just according to the blum blum shub random number generator. This is kind of the computation, and then the rest of the stream, well, we just recursively call our first function, just the Bbs generator. And our new seed is whatever the old number is, because that's how kind of the number generator actually works. Well, this looks like a really short and easy function, and it doesn't look like it's going to do anything. So what's actually what's going to happen when we run this? Well, let's create a new Bbs. So let's do that with val Bbs equals streamrand and let's just say the number is 15, which is the multiplication of two primes, 3 and 5, and let's just put a seed of 3. So we have this new Bbs, and let's try doing some stuff with it. So let's do stream.cons of 9 and s1, and let's set that equal to stream.expose of Bbs. So as you can see, this checks out because it doesn't give us an error, which means that the first iteration of our Bbs generator fits with this. So basically 9 is the first number. If we do this again, we can do stream.expose s1. As you can see, the next value is now 6. If we then do stream.cons of, instead of exposing Bbs, we now expose our s1. And we can store this in something called s2. We put the semicolon there. We have a bind failure. And that makes sense because this is supposed to be 6 here. As you can see, this passes. And if we do stream.expose, let me go up in the command, and expose now s2, as you can see, it's 6 again. And if you actually do the BBS number generator, you will see that it keeps being 6 with this initial set of numbers. Kind of cool, right? So as you can see, we can have infinite recursion without crashing your computer because the whole point of lazy programming is delaying computation, which lets us not have any issues like Stack Overflow. Thanks for watching, and if you enjoyed or you learned something, please leave a like or comment down below if you're confused or if you want me to explain some more. Bye, thank you!